Every day, your eyes convince you that the universe is simple. You wake up, walk through solid walls of certainty, touch objects that feel unquestionably real, and move through spaces that seem completely empty. Your mind quietly accepts this picture without resistance because it is comfortable. It is efficient. It keeps you alive. But comfort and truth have never been the same thing. The reality hidden beneath your everyday experience is so profoundly different that, if you could perceive it directly, your entire understanding of existence would collapse in an instant. Look around you for a moment. The air between your hands appears empty. The darkness between stars appears empty. The enormous distances separating galaxies appear empty. Your instincts insist that these places contain nothing of importance. That assumption feels so obvious that questioning it almost sounds absurd. Yet this single assumption has misled humanity for thousands of years. The greatest discoveries in modern physics have forced scientists to abandon the very idea that emptiness is simply the absence of everything. Instead, what appears to be nothing has become one of the most fascinating subjects ever explored. This is where your intuition begins to fail. Your brain did not evolve to understand quantum mechanics, spacetime, or the deepest architecture of reality. It evolved to recognize danger, find food, avoid predators, and survive long enough to pass on its genes. Evolution rewarded useful perception, not perfect perception. Your senses are not windows into objective reality. They are survival tools that simplify an unimaginably complex universe into a version your brain can process. That simplified version works remarkably well for crossing a street or catching a falling object, but it becomes hopelessly unreliable when you begin asking what reality actually is. The uncomfortable truth is that what you call reality is only a filtered experience. Your eyes detect a tiny fraction of the electromagnetic spectrum. Your ears capture only a narrow band of vibrations. Your skin senses only certain forms of pressure and temperature. Beyond those limits exists an enormous universe your senses never reveal. If your own perception hides so much from you, why should you assume it tells the truth about empty space? That question changes everything. For centuries, people imagined space as an enormous empty container where stars, planets, and galaxies simply floated around like objects inside a giant box. It seemed logical. Remove every object from the box, and eventually nothing should remain. Simple. Elegant. Completely wrong. Modern physics has steadily dismantled that comforting picture, replacing it with one that is far stranger and infinitely more profound. Empty space is no longer viewed as passive emptiness. It possesses structure, properties, measurable effects, and behaviors that influence the universe on every scale. The stage itself is part of the performance. Here is the first harsh realization that challenges almost everything you instinctively believe: what you cannot see is often far more important than what you can. Human history repeatedly demonstrates this lesson. Gravity was invisible long before it was understood. Magnetic fields existed long before anyone knew how they worked. Radio waves filled the world before receivers could detect them. Entire galaxies remained hidden until better instruments revealed them. Reality has never been limited by the boundaries of human perception. Every generation that believed it had reached the limits of knowledge eventually discovered how little it truly understood. The second harsh realization is even more unsettling. Everything you consider solid depends upon something that appears empty. Every atom, every molecule, every planet, every living cell, and every star exists within a universe whose invisible structure is just as essential as the matter it contains. Without that structure, the laws governing nature would not operate in the way they do. Motion would lose meaning. Light would not travel as it does. Gravity would not shape the cosmos. The universe you know could not exist. Think about the significance of that idea. The greatest foundation of reality is not something your eyes can point toward. It is something your instincts overlook every second of your life. Humanity has spent centuries focusing on objects while largely ignoring the medium that makes those objects possible. Physics has gradually reversed that perspective. Instead of asking only what matter is made of, scientists began asking what space itself really is. That single shift opened entirely new chapters of discovery, revealing mysteries that continue to challenge even the most advanced theories. This is not merely an abstract scientific discussion reserved for laboratories or textbooks. It is a challenge directed at the way you think. If your own senses can deceive you about something as fundamental as emptiness, what other assumptions have you accepted simply because they felt obvious? How many beliefs survive only because they have never been questioned deeply enough? Progress has always belonged to those willing to doubt appearances. Every revolutionary discovery began with someone refusing to accept that the obvious explanation was the correct one. The universe has a habit of humiliating certainty. Every time humanity declares reality to be simple, nature reveals another hidden layer beneath it. Every time we believe we have reached the end of understanding, another mystery emerges from what once appeared ordinary. Empty space is perhaps the greatest example of this pattern. What once seemed like nothing has become one of the deepest mysteries in all of science, forcing us to rethink matter, energy, time, gravity, and even the meaning of existence itself. By the time this journey is over, you will never look into the darkness between stars, or even the empty air surrounding you, in the same way again. You will realize that the greatest secret of the universe is not hidden inside distant galaxies or exotic particles. It is hidden inside the very thing your mind has ignored since the day you were born. The greatest illusion was never believing that something exists. It was believing that nothing ever truly could. The greatest obstacle to understanding the universe is not the lack of intelligence. It is the confidence that your everyday experience accurately reflects reality. Every moment of your life reinforces the belief that solid objects are completely filled with substance and that empty space is simply the absence of everything. It feels undeniable because your senses never give you a reason to question it. You push against a wall, and it resists. You pick up a stone, and it has weight. You stand on the ground, and it supports you. Your brain concludes that matter is dense, continuous, and completely solid. Yet this conclusion begins to unravel the moment physics examines nature on its smallest scales. Take a single atom, the fundamental building block of ordinary matter. It is tempting to imagine it as a tiny solid sphere, packed tightly with material. That mental picture is simple, but it is profoundly misleading. An atom consists of an incredibly small nucleus surrounded by electrons that occupy regions of space described by quantum mechanics. Between the nucleus and those electrons lies an astonishing amount of what appears to be empty space. If the nucleus were enlarged until it became the size of a marble placed in the center of a massive stadium, the electrons would exist far out near the edges, leaving almost the entire interior seemingly vacant. The proportions are so extreme that they challenge human imagination. Now consider what this means. Every object you have ever touched, every mountain, every ocean, every building, every tree, and every cell in your body is constructed from atoms. If atoms are overwhelmingly composed of what appears to be empty space, then everything around you is far less solid than your senses suggest. This is not a philosophical metaphor or a poetic way of describing reality. It is a consequence of how matter is structured at the atomic level. The solidity you experience is not created because particles are packed tightly together like grains of sand. It emerges from the interactions governed by the laws of electromagnetism and quantum mechanics. When your hand presses against a table, the atoms inside your skin never truly merge with the atoms inside the wood. Instead, negatively charged electrons surrounding those atoms repel one another through electromagnetic forces. At the same time, quantum mechanical principles prevent identical particles from occupying the same quantum state under identical conditions. The sensation your brain interprets as physical contact is actually the result of these invisible interactions occurring at unimaginably small scales. What feels like two solid surfaces touching is, in reality, an intricate balance of fundamental forces operating with extraordinary precision. This realization exposes one of the most persistent illusions in human experience. Your senses tell you that matter itself creates solidity. Physics reveals that solidity is better understood as the consequence of relationships between particles and fields rather than the simple presence of material substance. Reality is governed less by tiny objects behaving like miniature billiard balls and more by interactions that your eyes can never directly observe. The universe is not built from isolated pieces existing independently. It is built from connections, forces, and structures working together according to mathematical laws that remain consistent across the cosmos. The implications extend far beyond the atom. Once you recognize that matter itself is mostly empty space, another question naturally follows. If so much of the universe consists of apparent emptiness, can that emptiness truly be insignificant? For centuries, empty space was treated merely as a passive backdrop where physical events unfolded. It was considered a stage with no role in the performance. Modern physics has steadily dismantled that assumption. Space is no longer viewed as an inert container separating objects. It possesses measurable properties, influences the behavior of matter and energy, and participates in the fundamental workings of nature. This shift in understanding required scientists to abandon deeply rooted assumptions about how reality functions. Instead of asking only what matter is made of, they began asking what exists between matter. That question transformed physics. The emptiness between atoms, the immense distances between stars, and the vast void separating galaxies could no longer be dismissed as meaningless gaps. They became subjects of investigation in their own right. Every major advance revealed that space itself carries hidden complexity. The more closely researchers examined what appeared empty, the more evidence emerged that emptiness was anything but simple. There is an important lesson hidden within this discovery. Human intuition is an extraordinary tool for navigating everyday life, but it becomes increasingly unreliable as investigations move beyond ordinary experience. Nature does not shape itself according to what feels reasonable. It follows principles that remain true whether they satisfy human expectations or not. Again and again, science has advanced by replacing intuition with careful observation, mathematical reasoning, and experimental evidence. Every time evidence contradicted common sense, it was common sense that ultimately had to change. This is a difficult lesson because certainty is comforting. The mind naturally prefers simple explanations that match familiar experience. Yet history repeatedly demonstrates that reality is under no obligation to resemble the world as human beings first imagined it. The Earth is not the center of the cosmos. Time does not pass identically for every observer. Light behaves as both wave and particle depending on how it is measured. Matter itself is overwhelmingly composed of apparent emptiness. Each of these discoveries demanded the same intellectual courage, the willingness to abandon assumptions that once seemed unquestionable. The universe rewards curiosity far more generously than certainty. Every breakthrough begins with the recognition that appearances can be deceptive. Empty space seemed trivial until it became one of the most profound mysteries in science. Solid matter appeared simple until atoms revealed vast internal emptiness. The closer humanity has examined reality, the less ordinary it has become. What once looked like a collection of solid objects moving through empty nothingness has evolved into a vision of the universe where invisible forces, quantum behavior, and the hidden structure of space shape every aspect of existence. That transformation in understanding is only the beginning, because once the illusion of solidity disappears, an even deeper question emerges: if space is not truly empty, then what is actually filling it? Imagine removing everything from a sealed region of space. First remove the air. Then every atom. Every molecule. Every grain of dust. Eliminate every beam of light passing through it. Strip away every photon, every electron, every proton, every neutron. Continue until nothing that can be seen, touched, or measured as ordinary matter remains. Common sense insists that what is left must be absolute emptiness. It feels like the logical conclusion. If every particle has been removed, then nothing should remain. Yet this is precisely the point where classical intuition collides with one of the most astonishing discoveries in modern physics. Quantum physics refuses to accept the idea of perfect emptiness. According to our deepest theories, removing all particles does not produce a featureless void. Instead, what remains is known as the quantum vacuum, the lowest possible energy state permitted by the laws of nature. The phrase, lowest possible, is important because it does not mean zero in the everyday sense. It means there is no physically allowed state with less energy. Even in this condition, the universe does not become perfectly silent. The vacuum retains structure, properties, and activity that cannot simply be switched off. This idea initially sounds impossible because human experience has conditioned the mind to associate nothing with complete absence. An empty room appears still. A deserted road appears inactive. A dark night sky appears motionless. Everyday language reinforces the belief that emptiness is equivalent to inactivity. Nature tells a very different story. At the quantum level, complete stillness does not exist in the way intuition expects. Even the calmest possible vacuum exhibits subtle fluctuations that emerge from the fundamental behavior of quantum fields. These fluctuations are not objects suddenly appearing from nowhere in the ordinary sense. Rather, they reflect the restless character of quantum systems governed by the uncertainty principle. Certain physical quantities cannot simultaneously possess perfectly precise values. As a consequence, quantum fields cannot remain perfectly motionless, even in their lowest energy state. The vacuum behaves less like an empty container and more like a dynamic ocean whose surface continually experiences tiny ripples. From a distance the ocean appears calm, yet close examination reveals constant motion. The quantum vacuum displays a similar kind of hidden activity, although its behavior is governed by mathematics far removed from everyday experience. This restless nature of the vacuum has profound consequences. It means the universe is fundamentally incapable of becoming perfectly empty. The fabric of reality always retains an underlying level of activity. Even where no particles are present, the fields that permeate the universe continue to exist. Their lowest energy condition still possesses measurable physical significance. This completely overturns the ancient notion that nothingness is simply the absence of everything. In modern physics, the vacuum is not an empty stage waiting for actors to arrive. It is an active participant in the unfolding drama of the cosmos. One remarkable consequence of this understanding is that phenomena once considered impossible become natural outcomes of quantum theory. Certain observable effects can only be explained by acknowledging that the vacuum itself possesses physical properties. The famous Casimir effect, for example, demonstrates that two extremely closely spaced conducting plates experience a measurable force arising from the quantum nature of the vacuum. The effect is tiny, but it has been experimentally confirmed. This means the vacuum is not merely a mathematical convenience. It produces real, measurable consequences in the physical world. Another important implication concerns the stability of the universe itself. Empty space is not simply the absence of matter, it forms the environment in which every quantum field exists. Every particle known to science is associated with an underlying field extending throughout the universe. Even when no particles are present in a particular location, the fields remain. Their existence does not depend on matter occupying that region. In this sense, the vacuum is better understood as the quietest possible state of an already existing physical system rather than as genuine nothingness. This realization forces an extraordinary shift in perspective. Human intuition encourages the belief that matter is primary and empty space is secondary. Quantum physics suggests almost the opposite. The underlying fields exist everywhere, while particles are temporary excitations of those fields. In other words, the vacuum is not what remains after reality disappears. It is part of reality itself. Matter comes and goes. Particles are created and destroyed in countless physical processes. The fields remain. They provide the deeper framework from which the observable universe emerges. Perhaps the most astonishing lesson is philosophical as much as scientific. The closer humanity investigates the concept of nothing, the more elusive true nothingness becomes. Every attempt to define complete emptiness reveals another hidden layer of structure beneath it. What appeared to be absence becomes possibility. What appeared to be silence contains activity. What appeared to be emptiness possesses measurable influence. Nature repeatedly refuses to grant the existence of a perfectly featureless void. This challenges one of the oldest assumptions in human thought. For centuries, people imagined that nothingness should be simple and existence should require explanation. Modern physics hints at something far stranger. Perhaps what we casually call nothing is already an extraordinarily rich physical state governed by laws, fields, and quantum behavior. If that is true, then the mystery is no longer why empty space contains something. The deeper mystery becomes whether absolute nothingness has ever been physically possible at all. The universe seems determined to blur the boundary between something and nothing, revealing that even the emptiest regions of existence are alive with hidden structure waiting to be understood. If empty space is not truly empty, then an even more important question demands an answer. What exactly is filling it? For centuries, the natural assumption was that matter represented the deepest level of reality. Everything that existed appeared to be built from tiny particles acting like miniature building blocks. The universe seemed comparable to an enormous machine assembled from countless individual pieces. The smaller those pieces became, the closer humanity believed it was getting to the ultimate foundation of existence. Yet as physics advanced through the 20th century, this picture began to collapse. The deeper scientists looked into nature, the less reality resembled a collection of isolated objects and the more it resembled an interconnected web of invisible fields stretching across the entire universe. Modern physics no longer treats particles as the most fundamental ingredients of existence. Instead, the Standard Model describes a universe permeated by quantum fields. These fields are not confined to specific locations or attached only to matter. They exist everywhere, extending throughout all of space. Whether a region contains a star, a planet, an atom, or seemingly nothing at all, the fields remain present. This single idea completely transforms the way reality is understood. Instead of imagining particles moving through an empty background, physics now describes particles as localized excitations of fields that already occupy the universe. A useful way to think about this is to imagine a perfectly calm lake stretching beyond the horizon. The lake exists even when its surface appears smooth. A wave is not something separate from the lake. It is simply a temporary disturbance traveling through water. When the wave disappears, the lake remains exactly where it was. In much the same way, what we call an electron is not an independent object floating through emptiness. It is a localized excitation of the electron field. A photon is an excitation of the electromagnetic field. Other elementary particles arise from their own corresponding quantum fields. The particles appear, interact, and sometimes vanish, but the fields themselves persist everywhere. This shift in perspective is one of the greatest revolutions in scientific thought. For thousands of years, reality was understood primarily in terms of objects. The emphasis was always placed on things that could be seen, touched, or measured directly. Quantum field theory redirects attention away from objects and toward the invisible structures from which those objects emerge. The fields become primary. The particles become secondary. Matter itself is no longer viewed as the ultimate substance of the universe but as temporary patterns within deeper, all-pervading fields. This idea may seem abstract, but it explains an enormous range of physical phenomena with extraordinary precision. Every interaction between fundamental particles occurs because of these underlying fields. When electrons repel one another, it is not because tiny solid spheres are pushing apart. Their behavior is governed by the electromagnetic field. When light travels across billions of light-years through interstellar space, it does not move through absolute nothingness. It propagates as a ripple in the electromagnetic field that fills the universe. Even the forces responsible for radioactive decay and many nuclear interactions arise through corresponding quantum fields. The more closely nature is examined, the clearer it becomes that fields are not mathematical inventions. They are essential components of physical reality. Perhaps the most remarkable consequence of this understanding is that the vacuum itself can never be separated from these fields. Even if every detectable particle were somehow removed from a region of space, the fields would remain. They cannot simply be erased while leaving space behind. This means that what appears to be empty space is already occupied by the fundamental framework responsible for every known particle and interaction. Empty space is therefore not an absence of reality. It is reality in one of its quietest possible forms. The implications extend even further. The famous Higgs field provides a striking example of how deeply these invisible structures influence the universe. Unlike many fields that become noticeable primarily through their particles, the Higgs field possesses a non-zero value even in its lowest energy state. Every fundamental particle constantly interacts with this field to varying degrees, and those interactions contribute to the masses of many elementary particles. Without the Higgs field, the universe would look radically different. Atoms could not form in the familiar way, chemistry would not exist as it does, stars would evolve differently, and life itself would almost certainly be impossible. The invisible background of space is therefore not merely supporting the universe, it is helping determine the properties of everything within it. This realization forces a profound change in perspective. Human intuition naturally encourages the belief that reality consists primarily of visible objects surrounded by empty gaps. Quantum field theory reverses that relationship. The invisible fields are continuous and universal, while the visible particles are temporary manifestations arising within them. The universe resembles an immense symphony of interacting fields, with particles appearing as brief notes played upon an underlying cosmic instrument. What seems permanent from everyday experience is often temporary at the deepest level, while what appears invisible proves to be the enduring foundation of existence. The history of science repeatedly demonstrates that progress occurs whenever humanity abandons familiar pictures of reality in favor of evidence. The Earth was once believed to be stationary because it appeared motionless beneath our feet. Time was once assumed to flow identically for everyone because daily experience suggested nothing else. Matter was once imagined as the fundamental substance because nothing seemed more obvious. Each of these assumptions eventually yielded to discoveries that revealed a deeper truth. The recognition that fields, rather than particles alone, form the underlying fabric of nature belongs among the greatest of these intellectual revolutions. The deeper this understanding becomes, the more extraordinary the universe appears. Space is no longer a passive emptiness separating objects. It is an active, structured medium filled with invisible fields whose existence makes every atom, every beam of light, every chemical reaction, and every living organism possible. The universe is not built upon emptiness but upon an intricate network of hidden structures extending through every corner of existence. What once appeared to be nothing has become one of the richest and most fundamental aspects of reality, revealing that the invisible architecture of space may be even more important than the matter it contains. Darkness has always deceived the human mind. When you look into the night sky, your instincts tell you that the blackness between the stars is empty. It appears silent, motionless, and lifeless. Your eyes naturally focus on the bright objects, the stars, the planets, the glowing galaxies, while the immense darkness surrounding them seems insignificant. Yet this simple observation hides one of the greatest misconceptions in science. The universe is not defined by the things you can see. In fact, the visible matter that forms stars, planets, oceans, mountains, and even your own body accounts for only a small fraction of the total content of the cosmos. The vast majority of reality remains invisible, and the darkness that appears empty is far more active than your senses could ever reveal. One of the most extraordinary discoveries in modern physics is that empty space possesses energy even when it appears completely devoid of matter and light. This energy is commonly referred to as vacuum energy. Unlike the energy stored inside a battery or the energy carried by moving particles, vacuum energy is associated with the lowest energy state of quantum fields themselves. At first glance, this idea sounds contradictory. How can the lowest possible energy state still contain energy? Everyday experience teaches that when everything has been removed, nothing should remain. Nature refuses to obey that expectation. Quantum mechanics predicts that the vacuum can never become perfectly inactive because the fields permeating space cannot simply cease to exist. This conclusion emerges from one of the central principles of quantum theory. At microscopic scales, complete certainty is impossible. The uncertainty principle places fundamental limits on how precisely certain pairs of physical properties can be defined simultaneously. As a consequence, quantum fields cannot remain perfectly motionless. Even in their lowest energy state, they undergo continuous microscopic fluctuations. These fluctuations are not signs of imperfection in the theory, they are natural consequences of the mathematical framework that has successfully explained countless experimental observations with astonishing accuracy. The vacuum therefore behaves less like an empty container and more like a dynamic system whose quietest possible condition still contains subtle activity. The remarkable aspect of vacuum energy is that it is not merely a theoretical curiosity. Its effects appear in measurable physical phenomena. One of the clearest examples is the Casimir effect, where two extremely closely spaced conducting plates experience an attractive force because the quantum vacuum behaves differently between the plates than outside them. This tiny force has been measured repeatedly in laboratory experiments, providing compelling evidence that empty space possesses physical properties. The vacuum is not simply an abstract concept used in equations. It produces observable consequences in the real world, demonstrating that what appears empty can exert genuine influence. As scientific understanding deepened, researchers began asking an even more ambitious question. If the vacuum possesses energy on microscopic scales, could this energy also influence the universe on the largest possible scales? Observations of distant supernovae in the late 20th century revealed something astonishing. Instead of slowing down under the pull of gravity, the expansion of the universe is accelerating. Galaxies separated by billions of light-years are moving away from one another at an ever-increasing rate. This discovery transformed modern cosmology because it implied that some form of energy is acting against gravity across the entire universe. The exact nature of this cosmic acceleration remains one of the greatest unsolved mysteries in physics. One possible explanation involves vacuum energy itself, represented mathematically by what is known as the cosmological constant. If empty space possesses an intrinsic energy density, then as the universe expands and more space comes into existence, the cumulative effect of that energy could drive the accelerated expansion observed by astronomers. Although the precise relationship between vacuum energy and cosmic acceleration remains an active area of research, the possibility illustrates an extraordinary idea: what appears to be empty nothingness may influence the evolution of the entire cosmos. This realization forces a dramatic shift in perspective. Human intuition naturally assigns importance to visible objects because they dominate everyday experience. Stars attract attention because they shine. Planets appear significant because they possess mass. Galaxies seem extraordinary because of their immense size. Yet modern physics increasingly points toward the invisible background as one of the most influential components of reality. Space itself may contain energy capable of shaping the destiny of the universe. The emptiness between galaxies may contribute more to cosmic evolution than the galaxies themselves. History repeatedly demonstrates that invisibility should never be mistaken for insignificance. There was a time when electricity flowed unnoticed through nature because no instrument existed to detect it. Magnetic fields influenced matter long before humanity understood magnetism. Radio waves filled the Earth before radios were invented. Neutrinos streamed through planets for billions of years before they were directly observed. Again and again, science has revealed that the universe is governed by phenomena hidden beyond ordinary perception. Every generation that assumed visible reality represented complete reality eventually discovered another invisible layer beneath it. The same lesson applies to empty space. Darkness is not proof of absence. Silence is not proof of inactivity. An inability to perceive something does not diminish its importance. The universe consistently reminds humanity that appearances are unreliable guides to fundamental truth. The deeper researchers investigate reality, the more they encounter hidden structures operating beyond the reach of ordinary senses. What once seemed to be featureless emptiness now appears as an arena filled with quantum fields, fluctuating energy, and physical properties that influence everything from microscopic particles to the expansion of the observable universe. Perhaps the greatest lesson is not merely scientific but intellectual. The human mind instinctively searches for certainty in what it can directly observe, yet nature repeatedly rewards those willing to question appearances. Empty space teaches that absence is often an illusion created by limited perception. The blackness between the stars is not a cosmic void waiting to be filled. It is an active participant in the universe, carrying hidden energy and profound mysteries that continue to challenge the deepest theories of physics. Every new discovery pushes humanity toward the same conclusion: the universe is far richer than the eye can ever reveal, and what appears to be nothing may ultimately prove to be one of the most powerful realities of all. For most of human history, space was treated as nothing more than an empty stage. Matter was considered the main character, while space simply provided a place where events happened. Planets moved through it. Stars occupied it. Light traveled across it. It seemed passive, silent, and completely unaffected by the objects it contained. This picture appeared so obvious that questioning it hardly seemed necessary. Yet one of the greatest revolutions in physics revealed that this intuitive view is fundamentally incomplete. Space is not merely the backdrop of the universe. It is an active part of reality, capable of influencing matter, energy, light, and even the flow of time itself. The first major challenge to the old picture emerged from the realization that gravity is far more than an invisible force pulling objects together. In everyday life, gravity appears simple. Drop an object, and it falls. Throw a ball, and it follows a curved path back toward the ground. Watch the moon, and it circles the earth with remarkable precision. For centuries, these motions were successfully described as the result of gravitational attraction acting across space. While this explanation predicted motion with extraordinary accuracy, it left a deeper question unanswered. What exactly was gravity, and how did it operate across seemingly empty space? A profound shift occurred when physicists began treating space and time not as separate entities but as components of a single four-dimensional structure known as spacetime. Instead of imagining gravity as a mysterious force reaching invisibly between distant objects, modern physics describes massive bodies as influencing the geometry of spacetime itself. Matter and energy alter the structure of spacetime, and that altered geometry determines how objects move. In this picture, planets are not being pulled through an empty void by invisible strings. They follow the natural paths defined by the curved geometry surrounding massive objects. This concept can initially seem abstract because human experience is shaped by flat surfaces and ordinary distances rather than the geometry of spacetime. Yet countless observations have confirmed this description with remarkable precision. The orbit of Mercury, which puzzled scientists for decades under earlier theories, is accurately explained by the curvature of spacetime around the Sun. Light passing near massive galaxies bends as it travels, producing the spectacular phenomenon known as gravitational lensing. Even time itself behaves differently in regions experiencing different gravitational conditions. Highly precise atomic clocks placed at different elevations tick at slightly different rates because gravity influences the passage of time. These are not theoretical curiosities. They are measurable consequences of the structure of spacetime. Perhaps the most astonishing implication is that space is no longer an empty container independent of the universe. It responds to the presence of matter and energy. Massive stars deform the geometry around them. Black holes create regions where spacetime becomes so intensely curved that even light cannot escape once it crosses the event horizon. On the largest scales, the expansion of the universe itself reflects changes in the geometry of spacetime over cosmic history. Every galaxy, every beam of light, and every planet moves within a structure that is dynamic rather than fixed. This understanding fundamentally changes the relationship between matter and space. Instead of treating matter as primary and space as secondary, modern physics reveals an intimate partnership between them. Matter tells spacetime how to curve, while spacetime tells matter how to move. Neither can be fully understood in isolation. The behavior of one depends upon the other. Reality is therefore not constructed from independent pieces interacting across an empty background. It emerges from a deeply interconnected system where geometry and matter continuously influence one another. The significance of this realization extends far beyond astronomy. Every moment of your life unfolds within the geometry of spacetime. The path followed by sunlight reaching your eyes, the orbit of Earth around the Sun, the operation of satellites providing global positioning, and the motion of galaxies across billions of light-years are all governed by the same underlying principles. Technologies such as the global positioning system must account for relativistic effects caused by both gravity and motion. Without correcting for these differences in the passage of time, GPS calculations would accumulate errors of several kilometers each day. What once seemed like an abstract feature of theoretical physics has become essential to modern technology. As scientists continued exploring the universe, they uncovered evidence that spacetime itself can behave in astonishing ways. Powerful astronomical events generate gravitational waves, tiny ripples in spacetime that travel across the cosmos at the speed of light. These waves were predicted long before they were directly detected. Their eventual observation marked one of the greatest achievements in experimental physics, confirming that spacetime is not an immovable framework but something capable of oscillating, stretching, and carrying energy across unimaginable distances. Even the fabric of reality can vibrate. This revelation forces another dramatic shift in perspective. Human intuition encourages the belief that space is empty because it appears invisible and featureless. Yet invisibility does not imply simplicity. Space possesses geometry. It can curve, expand, ripple, and influence the behavior of everything within it. The stage participates in the performance rather than merely supporting it. Every object moving through the universe is responding not only to other objects but also to the structure of spacetime itself. The deeper scientists investigate the cosmos, the clearer one lesson becomes. Reality is built upon relationships rather than isolated things. Matter cannot be separated from the field surrounding it. Gravity cannot be separated from the geometry of spacetime. Motion cannot be understood without considering the structure through which it occurs. Every attempt to isolate individual pieces of the universe ultimately reveals deeper levels of connection. The boundaries that once appeared obvious begin to dissolve, replaced by a vision of reality in which everything participates in a single interconnected framework. This transforms the meaning of empty space forever. It is not an inactive gap separating objects across the universe. It possesses measurable properties, responds to matter and energy, carries gravitational waves, determines the paths followed by light and planets, and shapes the evolution of the cosmos itself. The more closely humanity studies the universe, the more impossible it becomes to dismiss space as nothing. Instead, it emerges as one of the most fundamental ingredients of existence, proving that the greatest structures in reality are often the ones hidden from ordinary perception. The deeper science explores reality, the more it encounters a question that refuses to disappear. Every major discovery explains part of the universe, yet each answer exposes an even greater mystery waiting beneath it. Humanity has learned how stars generate light, how atoms form matter, how galaxies evolve over billions of years, and how the universe has expanded since its earliest observable moments. These achievements represent some of the greatest intellectual victories in history. Yet beneath every equation and every observation lies a question so profound that no existing theory has answered it completely. Why does anything exist at all instead of absolute nothingness? At first, this question appears deceptively simple. Everyday language treats nothing as an obvious concept. An empty room contains nothing. An abandoned road has nothing on it. A vacant field appears to contain nothing of interest. But modern physics has completely transformed this seemingly ordinary word. As the understanding of quantum fields, vacuum energy, and spacetime has advanced, scientists have realized that the nothing described by physics is not the same as the nothing imagined in everyday conversation. Even the emptiest region of space still contains quantum fields, physical laws, measurable properties, and the underlying structure of spacetime. If all of these remain, can it honestly be called nothing? This distinction is extraordinarily important because it changes the question itself. A quantum vacuum is not absolute non-existence. It is a physical state governed by mathematical laws. It possesses structure, energy, and behavior. Absolute nothingness would be something far more radical. It would mean the complete absence of space, time, matter, energy, quantum fields, physical laws, dimensions, mathematical relationships, and even the framework within which questions can be asked. It is difficult to imagine because the human mind has never encountered such a condition. Every thought you have depends upon concepts that already assume existence. Trying to picture absolute nothingness is like trying to see without sight or think without consciousness. The mind reaches its own limits. This is where one of the deepest philosophical and scientific mysteries emerges. If absolute nothingness contains no space, no time, and no laws of physics, then what could possibly cause a universe to appear? Cause and effect themselves require time. Processes require physical laws. Events require existence. Without any of these ingredients, the very language used to describe creation begins to lose meaning. Questions that seem perfectly reasonable suddenly become extraordinarily difficult to formulate. Asking what happened before the universe assumes that time already existed. Asking where the universe came from assumes that space already existed. These assumptions may not apply at the deepest level of reality. Modern cosmology has proposed several fascinating ideas in an attempt to understand the earliest stages of the universe. Some models suggest that the observable universe emerged from quantum processes operating under extreme conditions. Others explore the possibility of eternal inflation, where countless universes may arise within an ever-expanding cosmic framework. There are hypotheses involving quantum gravity, cyclic cosmologies, bouncing universes, and multidimensional scenarios inspired by advanced theoretical physics. Each of these models attempts to explain observations while extending the boundaries of current knowledge. Yet despite remarkable progress, none has achieved universal acceptance as the complete answer to why existence itself is possible. This uncertainty should not be mistaken for failure. On the contrary, it reflects one of the greatest strengths of science. Genuine scientific inquiry does not pretend to possess certainty where evidence remains incomplete. Throughout history, progress has always depended upon acknowledging the limits of current understanding. There was a time when the motion of planets seemed inexplicable. There was a time when electricity, magnetism, and the nature of light were profound mysteries. Those questions eventually yielded to careful observation, experimentation, and mathematical insight. The unanswered questions of today may become the discoveries of tomorrow, but only if curiosity continues to replace certainty. Perhaps the most important lesson hidden within this mystery is intellectual humility. Human beings naturally seek final answers because uncertainty feels uncomfortable. The mind prefers certainty even when certainty is unjustified. Yet the history of science repeatedly demonstrates that reality is far more complex than first impressions suggest. Every generation has believed it stood near the summit of knowledge, only to discover an even greater landscape beyond the horizon. The deeper humanity explores nature, the larger the unknown becomes. Knowledge expands, but so does the recognition of how much remains unexplained. This realization carries an important warning. The greatest obstacle to discovery has never been ignorance. It has been the illusion of complete understanding. When people become convinced that every fundamental question has already been answered, curiosity fades. Questions stop being asked. Progress slows. Every revolutionary breakthrough in science began because someone challenged an assumption that everyone else accepted. The willingness to admit, we do not yet know, has repeatedly opened entirely new chapters of human knowledge. The mystery of existence therefore occupies a unique place in modern science. It reminds us that even the most successful theories describe only part of reality. Quantum mechanics explains microscopic phenomena with extraordinary precision. General relativity describes gravity and the large-scale structure of spacetime with remarkable accuracy. Yet these two pillars of modern physics remain difficult to unify into a single complete framework. The search for a deeper theory continues because nature consistently reveals that beneath every apparent answer lies another layer of reality waiting to be uncovered. When viewed from this perspective, the greatest mystery is not merely why empty space is never truly empty. The greater mystery is whether absolute nothingness has ever been physically possible in the first place. Every scientific advance has revealed more hidden structure where simplicity was once expected. The universe seems unwilling to allow complete emptiness. Instead, it continually replaces apparent absence with deeper layers of order, fields, geometry, and physical law. That possibility changes the way existence itself is understood. Rather than asking why something emerged from nothing, humanity may eventually discover that the concept of perfect nothingness was never physically meaningful to begin with. Until that question is answered, one of the greatest adventures in science remains unfinished, inviting every generation to continue searching beyond the limits of what is currently known. Every major scientific breakthrough has demanded the same sacrifice. It required humanity to abandon an idea that once felt completely obvious. The Earth appeared flat until evidence proved otherwise. The Sun seemed to move around the Earth until careful observation revealed the opposite. Time felt absolute until relativity demonstrated that it depends on motion and gravity. Matter looked solid until atomic physics exposed the vast emptiness hidden within every atom. Again and again, reality has shattered the assumptions created by human intuition. The lesson is impossible to ignore. The universe does not care what feels reasonable. It only follows the laws that govern its existence. This is perhaps the most important lesson hidden inside the mystery of empty space. The discovery is not simply about quantum fields or vacuum energy. It is about the danger of trusting appearances without question. Your senses evolved to help you survive in an ordinary environment, not to reveal the deepest structure of the cosmos. They provide an incredibly useful picture of reality, but they do not provide a complete one. The difference between usefulness and truth has shaped the entire history of scientific discovery. Consider how limited human perception truly is. Your eyes detect only a tiny fraction of the electromagnetic spectrum. Radio waves pass through your body without being seen. Infrared radiation surrounds every warm object, yet remains invisible. Ultraviolet light constantly reaches Earth from the sun, but your eyes cannot perceive it. X-rays travel through soft tissue while revealing hidden structures inside the body. Gamma rays carry enormous amounts of energy across the universe without ever appearing in ordinary vision. The visible colors that dominate human experience represent only a narrow window into an immense electromagnetic reality. If perception hides so much from you in something as familiar as light, why should you assume it accurately represents empty space? The same limitation applies to every other sense. Your hearing captures only a small range of sound frequencies. Countless vibrations occur beyond the limits of human ears. Your sense of touch cannot detect the quantum forces preventing atoms from passing through one another. Your awareness of time feels smooth and constant, yet atomic clocks demonstrate that time itself changes depending on velocity and gravity. Human experience creates the illusion of certainty because evolution optimized perception for survival rather than complete accuracy. Nature rewards organisms that react quickly, not organisms that understand quantum field theory. This realization carries a powerful intellectual lesson. Scientific progress has never depended on stronger opinions. It has depended on stronger evidence. Every major discovery emerged because someone questioned an assumption that everyone else accepted without hesitation. Curiosity has consistently defeated certainty. The history of physics is filled with moments when observations forced humanity to abandon deeply held beliefs. The willingness to replace intuition with evidence transformed our understanding of gravity, light, electricity, atoms, space, and time. Empty space became another victim of this process. What once appeared to be featureless nothingness gradually revealed itself to be one of the richest aspects of physical reality. There is another uncomfortable truth hidden within this journey. The greatest obstacle to understanding is often not ignorance but overconfidence. It is easy to recognize when you lack information. It is much harder to recognize when your confidence exceeds your understanding. Throughout history, civilizations repeatedly believed they had reached the limits of knowledge. Each generation assumed the fundamental questions had largely been answered. Yet every era eventually encountered discoveries that overturned previous certainty. The universe repeatedly humbled those who believed reality had become simple. This pattern continues today. Modern physics has achieved extraordinary success in explaining the behavior of matter, energy, and the evolution of the observable universe. At the same time, some of the deepest questions remain unanswered. The nature of dark matter is still unknown. The origin of dark energy remains one of cosmology's greatest mysteries. A complete quantum theory of gravity has not yet been established. The relationship between quantum mechanics and spacetime continues to challenge the brightest scientific minds. Every answer expands the boundaries of knowledge while simultaneously revealing new frontiers waiting to be explored. This should not discourage curiosity. It should inspire it. The existence of unanswered questions is not evidence of weakness within science. It is evidence that discovery is still alive. Science does not promise permanent certainty. It promises an ever-improving understanding based upon observation, mathematics, experimentation, and the willingness to revise conclusions when new evidence appears. That willingness to change is one of its greatest strengths. Reality is allowed to correct human belief instead of the other way around. Empty space teaches this lesson more clearly than almost any other subject. For thousands of years, people assumed emptiness required no explanation because it appeared to contain nothing. Modern physics revealed hidden fields, quantum fluctuations, measurable vacuum effects, and the dynamic geometry of spacetime. The closer scientists examined what seemed simplest, the more complex it became. Nature consistently hides its greatest truths beneath the assumptions people question the least. Perhaps the most valuable change this understanding can produce is not merely scientific knowledge but intellectual discipline. Learning to doubt appearances does not mean rejecting evidence. It means refusing to confuse intuition with reality. It means recognizing that certainty should always be proportional to the available evidence. It means remaining willing to revise even your strongest beliefs when observations demand it. This habit of thinking has driven every major advance in physics, from the motion of planets to the behavior of quantum particles. The universe has never rewarded complacency. It rewards curiosity, patience, and the courage to admit when familiar ideas no longer explain the evidence. Every mystery solved reveals another waiting beyond it. Every layer removed exposes a deeper one beneath. Empty space is no longer simply the absence of matter. It has become a reminder that the greatest discoveries often begin where human intuition reaches its limit. The moment you stop assuming reality must behave according to common sense is the moment you begin seeing the universe as it truly is, far stranger, far more beautiful, and infinitely more profound than appearances ever suggest. Take a moment to gather every idea explored so far and look at the universe through an entirely different lens. At the beginning, empty space appeared to be nothing more than the absence of matter. It seemed like a passive gap separating stars, planets, and galaxies. Then the illusion began to fall apart. Atoms revealed that what feels solid is overwhelmingly empty. Quantum mechanics demonstrated that the vacuum is never perfectly silent. Quantum fields showed that invisible structures exist everywhere, even where no particles are present. Relativity transformed space from a motionless background into a dynamic part of reality that bends, expands, and shapes the paths followed by matter and light. Piece by piece, the old picture disappeared. In its place emerged a universe that is far more interconnected than human intuition ever imagined. The most remarkable realization is that reality is not fundamentally built from isolated objects. Human perception naturally focuses on things. You notice mountains, trees, planets, stars, and people because your brain evolved to identify individual objects. Yet the deeper physics investigates nature, the less important isolated objects become. Instead, relationships begin to dominate the picture. Fields connect particles across space. Gravity emerges from the geometry of spacetime. Electromagnetic interactions determine the behavior of atoms. Quantum mechanics describes probabilities and interactions rather than tiny solid spheres following simple mechanical paths. Reality appears to be woven together by invisible relationships that are often more fundamental than the objects themselves. This represents one of the greatest conceptual revolutions in science. For centuries, the universe was imagined as a gigantic machine assembled from separate pieces. Every discovery seemed to reduce nature to smaller and smaller components. First came molecules, then atoms, then electrons, protons, neutrons, and finally the elementary particles described by modern physics. It seemed reasonable to believe that once the smallest building blocks had been identified, the deepest level of reality would be understood. Instead, physics revealed something unexpected. The smallest particles themselves arise from underlying quantum fields. Matter no longer appears to be the ultimate foundation. It becomes a manifestation of something deeper and more universal. This shift changes the way existence itself is understood. The universe begins to resemble a vast network of interacting patterns rather than a collection of independent objects. Every particle exists because of a field. Every orbit depends upon the geometry of spacetime. Every atom owes its stability to quantum principles governing the behavior of electrons and nuclei. Every galaxy evolves according to the interaction between gravity, matter, radiation, and the expansion of the universe. Nothing exists completely on its own. Every component participates in an enormous web of relationships extending across the observable cosmos. Perhaps the greatest irony is that humanity spent thousands of years searching for reality by looking only at visible matter. The deepest truths were hiding within the invisible framework supporting everything else. Empty space, once dismissed as insignificant, turned out to possess measurable properties, quantum activity, and physical influence on every scale. The foundation of existence may not be the objects occupying space but the underlying structures that make those objects possible. This reversal of perspective is one of the most profound achievements in the history of science. At the same time, this understanding reveals how much remains unknown. Physicists continue searching for a deeper theory capable of unifying quantum mechanics with general relativity. The nature of dark matter remains one of astronomy's greatest mysteries. Dark energy continues to challenge existing theories about the evolution of the universe. The earliest moments after the Big Bang remain only partially understood because the known laws of physics become extraordinarily difficult to apply under such extreme conditions. Every major breakthrough has answered important questions while simultaneously uncovering even deeper mysteries. This should not be viewed as evidence that science has failed. Quite the opposite. The expanding frontier of unanswered questions demonstrates that reality is richer than any single theory can currently describe. Every generation inherits a more detailed understanding of nature than the one before it, yet every generation also discovers entirely new mysteries. Progress does not eliminate wonder. It magnifies it. The closer humanity approaches the foundations of existence, the more astonishing those foundations become. There is also an important lesson about the nature of knowledge itself. Many people imagine science as a collection of permanent facts carved into stone. In reality, science is better understood as a process of continuous refinement. Every theory remains open to revision if new evidence demands it. This willingness to improve existing explanations is not a weakness. It is precisely what allows scientific knowledge to become increasingly reliable over time. Confidence is always earned through evidence rather than protected from it. That commitment to evidence has transformed empty space from an overlooked concept into one of the most active areas of modern research. The journey through the mystery of empty space ultimately reveals something much larger than a collection of fascinating scientific facts. It demonstrates that the universe consistently rewards deeper questions. Every time humanity believed it had reached the simplest explanation, another hidden layer emerged beneath it. The history of physics is a history of discovering that reality is more interconnected, more subtle, and more beautiful than appearances suggest. The visible universe is only the surface of a far deeper structure extending beyond the reach of ordinary perception. This leads to one final realization before the journey concludes. The greatest illusion was never believing that empty space contained nothing. The greater illusion was believing that reality could ever be fully understood through appearances alone. Every atom, every beam of light, every galaxy, and every region of seemingly empty space points toward the same truth. Existence is built upon invisible structures operating according to laws that continue to surprise even the brightest scientific minds. The universe is not merely stranger than people once imagined. It continues to reveal that it may be stranger than human intuition is naturally prepared to comprehend. Every discovery about empty space is therefore also a discovery about the extraordinary depth of reality itself, reminding us that the greatest secrets of the cosmos are often hidden within the things we once considered ordinary. You began this journey believing that empty space was simply the absence of everything. That belief felt natural because your senses encouraged it every day of your life. You looked at the darkness between the stars and saw nothing. You looked at the air surrounding you and assumed it contained no deeper mystery. Yet step by step, that comfortable picture collapsed. What first appeared to be a silent void revealed itself as one of the most extraordinary features of the universe. The emptiness inside atoms challenged the meaning of solidity. Quantum mechanics exposed the restless activity hidden within the vacuum. Invisible quantum fields replaced the idea of isolated particles as the deepest layer of reality. Spacetime itself emerged as an active participant in the evolution of the cosmos rather than a passive stage upon which events merely unfold. The deeper the investigation reached, the less meaningful the word empty became. Perhaps the greatest lesson from this exploration is not simply that space is filled with hidden structure. It is that reality consistently refuses to match human expectation. Again and again, the universe has demonstrated that common sense is an unreliable guide to fundamental truth. What feels obvious often turns out to be incomplete. What appears permanent may emerge from something deeper. What looks simple may conceal astonishing complexity. Every revolutionary discovery in physics has required humanity to let go of familiar assumptions and replace them with evidence, no matter how uncomfortable the new picture seemed. That process is far from over. The universe continues to challenge every generation with questions that demand greater imagination, greater precision, and greater humility. One of the most remarkable aspects of science is that every answer creates new questions. Understanding the quantum vacuum immediately raises deeper questions about the origin of quantum fields. Explaining spacetime leads to questions about the nature of gravity at the smallest possible scales. Discovering the expansion of the universe introduces mystery surrounding dark energy. Learning how particles acquire mass directs attention toward even deeper principles that may govern the fundamental laws themselves. Every horizon reached reveals another beyond it. The pursuit of knowledge is therefore not a journey toward the end of mystery. It is a journey toward ever greater layers of understanding where mystery becomes richer rather than smaller. There is a powerful lesson hidden within this pattern. Human history has repeatedly shown that certainty is temporary, while curiosity has lasting value. Civilizations once believed the heavens revolved around Earth. Later generations believed atoms were indivisible. Still later, scientists assumed space was an empty backdrop without physical significance. Each of these certainties eventually gave way to discoveries that reshaped humanity's understanding of existence. The willingness to question assumptions has consistently proven more valuable than the confidence of believing every answer has already been found. The future of science depends not upon defending familiar ideas but upon remaining open to evidence wherever it leads. This perspective extends beyond physics. Every meaningful discovery begins with the recognition that appearances can be misleading. The visible universe represents only a fraction of reality. Your senses capture only a narrow range of information. Your intuition evolved for survival rather than for uncovering the deepest architecture of existence. Recognizing these limitations is not a weakness. It is the beginning of genuine understanding. The moment you accept that reality is larger than immediate perception, you begin thinking like every great scientific explorer who has ever challenged the boundaries of knowledge. The mystery of empty space ultimately becomes a lesson about the extraordinary depth of the universe itself. What once seemed like nothing now appears as a foundation supporting matter, light, gravity, and the evolution of the cosmos. The invisible has repeatedly proven to be just as important as the visible. The spaces between galaxies are not meaningless gaps but part of the same interconnected reality that shapes every star and every atom. The universe is not constructed from isolated objects scattered through emptiness. It is built from relationships, fields, geometry, and physical laws extending across every corner of existence. Everything is connected by structures that remain hidden from ordinary experience yet determine the behavior of everything you can observe. At the same time, it is important to recognize how much remains unknown. Physicists continue searching for a unified description capable of reconciling quantum mechanics with gravity. The true nature of dark matter and dark energy remains unresolved. The conditions that existed during the earliest fractions of a second in cosmic history continue to challenge existing theories. These unanswered questions do not diminish the achievements of science. They highlight the incredible richness of reality and the limitless opportunities for future discovery. Every unanswered question is an invitation rather than a defeat. Now consider what this journey has quietly changed inside your own perspective. The next time you look into the night sky, you will no longer see empty darkness separating distant stars. You will recognize a universe filled with invisible quantum fields, shaped by the geometry of spacetime, governed by physical laws that continue to surprise humanity, and enriched by mysteries that have yet to be solved. The air surrounding you will no longer seem like an insignificant void. Even the apparent emptiness inside every atom will remind you that reality is infinitely more subtle than appearances suggest. Once this understanding takes root, it becomes impossible to return to the old picture of a simple universe made only of visible things. The greatest discoveries in history have never come from accepting the world exactly as it appears. They have come from asking deeper questions when everyone else believed the obvious answer was sufficient. That same opportunity still exists today. The universe has not finished revealing its secrets, and the greatest breakthroughs may still lie ahead. Every generation inherits mysteries from the one before it, and every curious mind has the chance to move humanity one step closer to understanding the extraordinary reality hidden beneath ordinary experience. If this exploration has changed the way you think about the universe, then do not let that curiosity end here. Share your thoughts in the comments and ask the biggest question that remains in your mind, because the most important discoveries often begin with a single question that refuses to disappear. If you enjoy exploring the deepest mysteries of physics, space, time, and reality through clear scientific explanations, subscribe and continue the journey. The universe has spent billions of years writing its story across the fabric of space itself. The only question left is whether you are willing to keep reading the next chapter.